In this video, we're going to go over variants of Minimax that extend it to environments and domains that don't fit the exact min-max or max-min structure that we've been looking at so far. So as a brief review, we talked about Minimax search. We talked about both in the video and in class. In class, we had an interesting discussion about how to adjust, or how we could imagine just adjusting Minimax to apply for settings that more than two agents exist, and maybe the agents have different objective values. So their goals are not exactly to minimize or maximize the max player's score, but maybe they have completely different utility functions. So it was an interesting discussion, and touches on some of the ideas this video will also cover. We also talked about the analysis of Minimax, and we saw that it's very similar in terms of computational complexity to depth-first search, and that should be no surprise because it's implemented mostly through this recursive argument or recursive way of thinking. So it's a stack-based algorithm. And then we didn't get to talk about alpha-beta pruning or the analysis of alpha-beta pruning, but we talked about alpha-beta pruning as an algorithm in the previous video and in class. And the analysis there, it really depends on the move ordering, and we didn't talk about this too much, but it's interesting to think about. If the move ordering is sort of completely adversarial, it's possible to design counterexamples where alpha-beta pruning does nothing. It doesn't help you in any way. But if the ordering is designed optimally, then you actually can argue with some analysis that you can basically half the computational cost of going a particular depth in the tree, which means that you can go twice as deep with the same amount of computation or memory, but only if the moves are ordered in a way that's most friendly, and in practice they're ordered in a way that's not necessarily all that friendly, and so it's hard to really pinpoint how much the improvement is in alpha-beta pruning. So in this video, we're going to go over, we're going to talk more about move ordering, which we discussed in class, and then we're going to get into games where there are unknown random events that affect the game state. So situations like where in a board game you might have dice rolls that determine how far a player can move, and there we'll talk about the Expectimax algorithm, as it's known, which is a variant of Minimax that takes into account these random actions that can occur in games. And then finally, we'll talk a little bit about partially observable games. I'll talk about some of these strategies that are possible for handling when you have unknowns, like truly unknowns that you can't observe in your state, in the game state. And that'll be rather open-ended because there isn't a really great solution, even though that pretty much characterizes every real situation that AI is going to try to solve in practice. So let's get to it. So in the Pac-Man homework problems, we're going to be dealing with situations where there are multiple ghosts and one Pac-Man. So we have the Pac-Man player is going to be our max player, and the ghosts are going to be min players. So in this case, there's two min players in this diagram, and then it repeats, right? So the max player gets to go again, and so obviously this doesn't fit the textbook's definition of the Minimax algorithm, right? We discussed this in class as well. In the textbook definition, you basically have a min move, and then a max move, and then a min move, and a max move. In this case, we have a max move, and then two min moves, and then a max move, and then two min moves. And so this gets to sort of why I initially showed in the last Minimax video, where we introduced Minimax, I showed pseudocode that looks kind of like this, where we have just a Minimax value. This is just a function that returns a value, a score. And it has this form of recursion where the decision of whether you choose the min or the max is determined in the function. It's determined based on which player's turn it is at state S. So, this differs from the textbook pseudocode. If you look at, this is from the textbook, you see that the max value function always calls the min value function, and the min value function always calls the max value function. But in this pseudocode, it depends on what the it depends on whose turn it is at the current time. So to implement this situation with multiple min players, you pretty much need to be more robust to whose turn it is in the current state. And then again, from the perspective of the current level of recursion, if you're the max player making a decision about which move to make, which move is my optimal move at this time, it doesn't matter what the min player is going to do after you, or the max player, or whatever player it is after you. It just matters that you've already computed through recursion, already computed the minimax value, or the optimal value, the score that you can achieve, assuming optimal play after this move, for each possible move, and then you make your decision based on that. So that's basically the form of this recursion. Now things get a little bit trickier, just a bit trickier when you implement alpha beta search in this form, because you have to think about how the bounds change depending on whether you have a min player or a max player as either a parent or a child. So that'll be again left as an exercise as part of the homework. It's pretty challenging, so just try to walk through small examples to make sure your logic and your code is implemented in a way that makes sense. Okay, so then let's get to the main new material in this video. So as I mentioned in class a few weeks ago, there was a lot of buzz because apparently researchers had found an algorithm or designed a computer system that was able to play poker, Texas Hold'em poker, better than any human, according to how they measured it. I'm not really sure how they measured it. And this is interesting because, for sure the tools that we've looked at so far don't allow us to do this, right? Minimax, we don't know how to handle poker for a number of reasons. One, the cards are random, right? So we don't know how to determine what the min player is going to do, because we need to know what cards they have, and what cards they have is determined by the randomness of the shuffle. And then also the other players intentionally trying to deceive us, right? There's a lot of deception. There's unknown things in the world, in the game state. What cards your opponent has, or your opponents at the table have, is unknown, and so we need to think about how to extend Minimax to be able to handle these additional complexities. So the first thing we're going to look at is just the randomness aspect. So the cards are randomly shuffled, or rather each time you draw a card, you get a random card from the deck that includes all of the remaining cards, all the cards that haven't already been drawn from the deck. Or in other games, you have dice. In one of the canonical examples is backgammon, which has a fairly famous history in AI research as one of the examples where people go to first as a game that kind of has similar discrete moves to chess, but throws in some randomness in the dice rolls. So the way we do this in what's called the Expectimax algorithm is we add a new player. So we have two players. We have min and max, and then we have this other weird player called the chance player. And the chance player, in the game tree, you can think of it as the chance player's turn is the dice roll, or the random shuffle of the cards, or the draw of the cards, if you want to model it that way. It's basically another turn where something random happens. And what's different about the chance player, what's different between, when you compare the chance player to the min and the max player, is that the chance player has no intelligence. It doesn't think about what it wants. It doesn't have a goal. It doesn't have utility. It doesn't want to minimize or maximize the max player's utility. All it does is some random action. So what you do need to know for a good implementation of the expected minimax algorithm is the probabilities of all the actions at the chance player's turn. Okay, and so what happens is then it's a pretty straightforward modification to the minimax code. This is a recursive formula for the expected minimax value. And you can see at the top it's got the same terminal condition, right? Where you go, if there's a terminal test, you use the utility score, or it could be a cutoff test if you want to do the approximation of the full expected minimax value. And then the max player does the same thing. It looks at the expected minimax values of the possible children it can reach through actions, and then the min player does does the same thing, and then they respectively choose either the maximum scoring option or the minimum scoring option. Okay, and then the last line, the fourth line of this case statement, is the chance player's turn. So if it's the chance player's turn, then rather than looking at all the actions and choosing one of them based on some objective, it just looks at all the actions and then computes the expected minimax score, the expected score of all of its children, given the probabilities of all the events in the chance node. So the backgammon tree from the textbook looks like this, where you have a max node at the top, a chance node right after that determines the sum of dice, I suppose, or rather the different ways you can have a combination of two dice land on certain numbers. And then the min moves after, or the min player moves after this dice roll happens. And if you think about you look at that same formula again, and you look at this tree, the way that it's structured, the analysis of this algorithm is pretty similar to minimax. All right, if you look at these operations, these max and min operations, they're just like in minimax. So again, you have to look at all, in true minimax, where we don't do any pruning, we have to look at all of the possible actions from any given state. So if you're the max player, you look at all the actions and you decide the maximum scoring action. If you're the min player, you look at all the actions and decide the minimum scoring action. But then the new operation is this sum, is this expectation, which is going to look at all the actions, look at the probabilities of those actions, and then do a weighted sum of the scores given those probabilities, or weighted by those probabilities. So again, just like the min and the max operations, you have to consider all of the states before you can make a decision. So in the min, you don't know until you reach the last state whether you've seen the truly minimum scoring state. So you always have to consider all of the states. You always have to consider the full branching factor. And then in the summation, in this expectation, in a fairly more obvious argument, in order to sum up all the entries in there, in this summation, you have to consider every entry. So given that there's now a different operation, right, the worst case, or the full expected minimax computation, we know it requires considering every single state in the entire game tree. We also know from discussion in class today that we can pretty much get away with a depth first evaluation. So the memory cost isn't that bad. Memory cost is fine because we can sort of accumulate the sum as we go. We don't have to remember the previous entries. We can just sort of sum them up, and we only need O of 1 storage for the total amount of score we've seen so far. But that's all. That's fine. The space is not too bad, but the time is really expensive. And we've alleviated the time complexity for minimax by doing alpha beta pruning. But can we do that here? It seems on the surface that it would be a lot harder, and in many ways it is. For the min and the max, we can do exactly the same thing that we've done previously with alpha beta pruning, but for the sum nodes, for the chance nodes, where we have to sum up these expectations, it gets a little bit, or we have to be less aggressive with pruning, because it's hard to tell when we can lower or upper bound an expectation, or rather, we can tell, but the bounds don't cut off as quickly as they do when we're doing a min and the max. So let's think about how we can bound the expected value of a bunch of moves. Right? We have b possible moves, and we have to consider each of them and sum them up and multiply them by their probabilities. And we want to bound what that total sum is going to be before we see all of the options. So imagine this example. So we're just going to consider a uniform die. So we're going to roll a 6-sided die, one of the standard ones you get for most board games. And it's uniform probability, so it's a fair die. And we have a utility score that ranges between -10 and 10. So the utility score, we can compute the expected minimax value. Let's just assume recursively that we can compute the expected minimax value for the children given the dice roll, the die roll. Okay, so let's see what happens when we roll the first, or rather we consider what happens if the die lands on 1. Let's say we compute the score of the child given 1, and we get that the score is 10. So the score is the maximum possible utility for that scenario. So let's think about now how we can bound the total expectation for all of the other cases, not just 1, but 1, 2, 3, 4, 5, 6. So what is the way to bound this? Well, we can think about what the best case scenario is for the max player. So the best case is the rest of the rolls are also, or the rest of the situations are also utility 10. They also give us a minimax score, expected minimax score of 10. And if that's the case, then the total expectation could be 10. Right? In the best case scenario, we can still have a expected minimax score or an expectation of 10. So we actually didn't gain anything there because our bound is the same as the bounds on the total utility score anyway. All right, and then the worst case scenario is now that all of the die rolls that can occur, other than the one that we've evaluated, are -10, are the minimum possible utility. And if that's the case, then our expectation is -0.667, which that's really good news, because we actually have a non-vacuous bound. We can say that given just what we've observed in this first die roll, we already know that the expected value is going to be something between -0.667 and 10. Okay, and we can continue. If we see another die roll, we try the result of 2, and we get that is also 10. That's, again, good news for the max player. The best case scenario doesn't change; it's still all 10s. But then the worst case scenario gets a little bit better. In the worst case scenario, the rest of the states we haven't evaluated yet are -10, which means the expectation can be no greater than, or rather the expectation in the worst case is -0.33, which means that regardless of what the actual utility values of the remaining states, the worst case bound has to be at least as great as -0.33. Okay, and this can continue. Suppose we evaluate the state for the die roll of 3, and we get that now the best case scenario, filling in the best utility value for the remaining unknown scores, we get an expectation of 6.67, and the worst case remains the same, remains the same as before, of -3.33. And so if we use these bounds as our alpha-beta bounds, the same algorithm works just as well. Alpha-beta pruning works exactly the same way, as long as we're computing the bounds, with this procedure for any of the chance nodes. And just from this example, you probably got to see the intuition that this doesn't shrink the bounds nearly as fast as the min and the max nodes do. And as a result, adding in these chance nodes is necessarily, or not necessarily, but is very likely to make alpha-beta pruning not work as well as it would have in a truly deterministic min-max scenario. And furthermore, there's another assumption I made in this example that is necessary to make this work. So imagine that we have an expect-a-minimax algorithm, or we're trying to bound expectations. We can even just simplify it to just trying to bound expectations. But the utility score ranges from minus infinity to positive infinity, right? The utility score is unbounded. Now, in that situation, do we know anything about the upper and lower bounds? If we've observed, let's say we observe all but one state. We're at the point where we've seen a 10, a 10, a 10, a 10, a 10, a minus 10, a 10, and a 10. And then the last one's a question mark still, right? If we are in that situation, do we know anything about the expected value? So the answer is no, because that value could be minus infinity, right? If that utility value is minus infinity, the expected value is minus infinity. If that value is positive infinity, the expected value is positive infinity. So given that we have an unbounded utility function, we don't know anything about that final expectation. So another strategy we can take, instead of using expect-a-minimax, is to replace all the chance actions with deterministic outcomes that we sample from a random distribution. So rather than simulating every single possible outcome of every die roll, we could instead just randomly choose a dice, a value for our dice or die, depending on the game, and run minimax as if it was a deterministic game, as if the dice have already been determined by some oracle, right? And this is similar to our concept of how when we replace the min player with an oracle, minimax becomes just search, or becomes a form of search, just like from our the first segment of the course. In this way, if we replace the chance nodes with a deterministic sequence of the actions that can occur in the chance nodes, this reduces to regular minimax, but it doesn't tell us, it only tells us what our minimax optimal strategy should be for that particular sequence of dice or of random events. So in order to really get this to work, with the randomness that occurs in these chance nodes, you have to do lots and lots of samples. But the good news is that you can kind of get away with choosing how many samples you're willing to compute and making the best decision given the data you collect running that many samples, right? So rather than committing to expect a minimax, which might take a super long time to compute all the outcomes and to compute those expected values, you can just run a bunch of samples and then make the best decision you've found so far from the samples, or given the distribution you can estimate, the probabilities you can estimate from the samples. And then if we have partial observations, we can kind of take a similar approach. So the idea, one idea for handling partial observations, and this is not, for sure, is not the only way to do things, and is almost certainly not the best way to do things, but it's a simple way to get started, is to simulate perfect information with chance nodes. Rather, whatever information you don't get to see. So let's say you're playing poker, you don't get to see your opponent's cards. But what you could do is you could simulate a chance node that is the shuffling of the deck at the beginning of the hand, or the round, or it depends on what game you're playing. But the idea is there's one random event. The one random event shuffles all the cards, and the rest is deterministic, right? Everything is deterministic at that point, because let's say the deck has already been ordered, and we can, our computer program can write down that order and read off that order deterministically. So what you would do is you'd have a single chance node at the beginning that shuffles the cards into a random order, and then you have regular old minimax afterwards. And then in that, this would be a weird representation of the world of poker, because in that world of poker, everyone would be playing minimax knowing exactly what cards everyone else has, which doesn't make too much sense. So that's one reason why this method doesn't always work in games of deception, but it works fairly well in games where it's not deceptive. It's not about deception, but it's about there's just some information you don't have. And if you think about other reasons why this strategy isn't ideal for poker, if you think about the shuffle order of the cards, the number of possible orderings you can have is this expression. It's 52 factorial, which is a huge number, not something that we will likely ever be able to represent on reasonable hardware. And what you can do, though, is you might use some approximation in the early stages of the game, but maybe as you observe, as you see cards between shuffles, if the the game playing program or the casino doesn't shuffle between every hand, you might see a bunch of cards during the run of the game, and that will reduce the possible orderings you have to worry about down significantly. Still to a huge number, but something, the difference between those two numbers is so big that it sort of elucidates the advantage of card counting in card games, right? So those of you who probably know that card counting is a major strategy in blackjack, and if you can observe enough cards and you have a nice system to keep track of it in your head, you can increase your probability of winning to the point where you can actually make a profit in the long run. And then, you can imagine if you saw, so here in this case, if we've seen 20 cards, we can reduce the amount of possible orderings by about 33 orders of magnitude. And then if you see, 10 more cards, you can reduce it by another 9 orders of magnitude. But these numbers are still way too big for any computer program to reasonably handle. So you definitely need to come up with other strategies to handle partial observations. Maybe it involves sampling, maybe it involves some way of some compact representation of probability distributions that doesn't explicitly encode every every card ordering, but instead is more compact. And there's a lot of research on these sort of permutation representations that are more compact. Okay, so to summarize what we covered in this video, we talked about how minimax logic works for pretty much any move ordering, as long as you have a good way to identify whose turn it is at each decision point. And then expected minimax is an algorithm to extend minimax to situations where we have chance, we have randomness in the game, and it basically works just by adding a third type of player that is a chance player and uses an expected value. And then we talked about Monte Carlo simulations, so randomly sampling to simulate the chance nodes and not have to worry about exactly evaluating every single possibility, every single possible state given the chance nodes. And this is also important because a lot of the chance nodes tend to have a much higher branching factor than the player moves. This is natural because humans, you don't usually want to make the moves simpler when people design board games. You don't want to make it too complex for each player to decide what to do next. But when you have just a random draw from a deck, you don't really care how difficult it is for the random process to decide what move to go next. And then by using Monte Carlo sampling, you can alleviate that somewhat, but you do have to do a lot of sampling to get a good estimate of the probability. And then we talked about how we can apply these techniques to one way of handling partial information, of when information is not observed. You can basically model it as random and then try to do something like expected value over the unknowns. But it doesn't, and we also talked about how it doesn't fully translate to games where there's deception, where there's where the opposing player is intentionally trying to hide information from you and maybe acting in ways that make it look like the information that they are hiding from you is not what it seems. Okay, and so one thing I want you to think about for as you digest this video is this interesting discussion we had in class on Monday about how we can sort of design a variant of minimax where we just have players who act optimally according to their own definition of optimality, right? In this case, the chance player kind of behaves like that, right? The chance player in some ways chooses or is a further generalization of that, right? Rather than it choosing based on some different utility function, it does something different, which is that it chooses all the options but weights them according to the probability. So it sort of suggests that this framework of this recursive decision making could be extended into settings where there's randomness, where there's players or agents that have different goals, and parts of the environment that might have some intelligent decision making. And it's interesting to think about what other extensions we could come up with for Minimax. But so finish reading chapter 5, and we'll talk about any questions you have, and we'll hopefully get started on a new topic next class, but only after we make sure we cover everything there is to know that we need to know about Minimax. So see you in class.